Let's take a look at question 242 on Leet code, valid anagram. And this is going to be our first string problem that we're going to solve together. And we're going to solve this in a few different ways. And we're going to highlight some of the shortcomings of the string data type, in that the time complexity can quickly rise if you're not aware that you're doing certain string manipulations in a loop. So we're going to see that, and then we're going to see how we can solve this optimally. Given two strings, S and T, return true if T is an anagram of S and false otherwise. And an anagram is a word or a phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So let's have a look at this example here. We see the word anagram, and then we see the second input, nagaram. And you can see that each of these letters here, so the N here has been used, the A here has been used, the G here has been used, the second A has been used, and then A and the M, they've also been used. So all of the letters from the word S have been rearranged and are used to create this anagram word. And then there's an example of something that isn't an anagram. So we've got the words rat and car. So the R and the A, they're letters in T, but the T and the C aren't. So we're looking to see if T is an anagram of S. And by default, that means that S is going to be an anagram of T. So let's look at the code here. So let's see how we would solve this intuitively. So let's start by thinking about how we're going to solve the problem. And I think a good way to intuitively solve the problem is to keep track of the letters in S. And then as we cycle through T, we can do a lookup to see if it's in S or not. And if it is, we can remove it from S. So I think it would be a good idea to track the remaining letters in S. And I'm going to start by splitting the string, because we know we're going to do a bit of string manipulation here. And as we saw in the strings video, it's often a good idea to split the string into an array. And that way we're dealing with elements. And basically what I want to do here is I want to loop through each letter of T first, because for each letter, so let's say letter of T, what we want to do is we want to see if that letter is in the word S. So let's just say we want to get the S index. We can say, well, let's take our remaining letters S and let's find the index where the letter L, or for the letter L, if the letter from the remaining letters of S is equal to the letter in T, we can either get an index or we might not get an index. So if the S index, if it's less than 0, that means it's not defined or the index wasn't found. We can simply just go ahead and return false here, because it's not an anagram, because the letter wasn't found in S. Otherwise, what we'll do is for each iteration, we can go ahead and for the remaining letters S, which is originally all of the letters in S, we can go ahead and we can splice the letter that we found and remove one. So recall, splice does a mutation of remaining letters, so it will remove it, as opposed to slice, which doesn't mutate. And we find that by index, and then we remove one position to splice out or delete. So what we can do after this for loop is we can go ahead and we can return the remaining letters S, and if that length is equal to 0, that means we've looked at every single letter. And since there was no letters left, we have an anagram. Let's just go ahead and run this code just to see if it works or not. And we see that it has been accepted, but there's a limitation to this, and this is the reason I want to solve it this way, is because we've got a for loop here. So you might think that this is O of n, but then we've got this find index. So this is an O of n operation within a O of n, or a for loop. So the time complexity is actually going to be O of n squared. So the reason this is O of n squared is because every time we loop through the letter for the word T, for each letter, we need to determine if that letter is in the word S, which means we need to loop through each character in S, and then we find the index. And then that sort of compounds to a squared time complexity. We also have this splice here, and if you've seen the arrays video, if you delete something from somewhere in the array, you have to shift the other elements over. But in either case, we have an O of n squared, and we're making this array allocation here. So that's going to be O of n. So, okay, that's one way we can solve the problem. What's a simple way we can determine if it's an anagram? So this is much more simple, and you'd probably see this, or you probably might just code it like this if you're just coding, I don't know, if you're coding React or, you know, some web application, and you're not really trying to necessarily find a best time efficiency. You just want a simple one-liner or something like that. Basically, what you can do is you can just go ahead and you can say, well, we want to first split the array S. So we turn it into, the string S into an array of characters. And then what we can do is we can make use of the sort function, and then they'll sort all of the elements in the array. And because the each character has a ASCII number equivalent, and we're expecting characters, each characters thus are going to be ordered. So you can actually order all of the characters in the word, and then you can just join the string back up. So basically, that means if the word is an anagram, that means if you sort all of the letters in T, so let's just go ahead and copy this again for T, that means that these should be equal if it's an anagram. So let's just go ahead and run that one-liner, and that's a nice one because it's a one-liner. And it's better than O of n squared because we don't have any nested stuff going on, but it will be n log of n. So we haven't actually discussed sorting in details. We're going to do videos on all the different main sorting algorithms, and we'll see that JavaScript uses the best one, which is n log of n. So if we split our array, we're essentially assigning each variable or each character for the length of the array. So it's going to have O of n space complexity. It's because O of 2n simplifies back to O of n, plus we're joining again as well. But the sorting part here refers to, okay, well, we've got an array. If we perform a sorting algorithm on that array, that's going to be n log of n. And then we can just join all of that up. So of n log of n is better than of n squared, and the code's nice and readable. And this sort of highlights the trade-off between readable code and efficient code. But in this next and final example, we're going to determine how to solve this efficiently. So it's going to be more lines of code, but if you're dealing with large amounts of data and you need speed, then it's perhaps something that you would want. So you sort of got to make that trade-off, but in data structures and algorithms, of course, we're going for the best time complexity. So to be able to work out the best time complexity, we want to improve on of n log n. So basically, first we can do a couple of simple checks here. Basically, if the length is not equal to the length of the other word, we know straight up that it's going to not be an anagram because it can't be. And we also know that if the length is equal to 0, or the length of the other word is equal to 0, that won't be an anagram. So that's just getting the edge cases out of the way. What we want to do is we want to have a map. So I'm going to assign a variable here. I'm going to call it S character map, or S car or character count map. And I like to name my variables such that, or for maps such that they're in order of the things that we're mapping. So we're going to map the character, which is a string, to the count of that character, which is going to be a number. And we're going to see how we can use that. So basically what we want to do is we want to loop through all of our characters in S. And basically what we want to do is we want to get the character count. So I'll have a variable here and I'll call it character count. And well, actually, before I do that, what I might do is I might have a new character count, because initially there's nothing in our map. So basically, what I want to do is, well, I will need this actually. I first get the character count by looking at this map, and for the particular character that we're trying to look up, we want to use that information, because if that's defined, or we have found that character, we can say, well, the character count is simply going to be equal to what it is, plus 1. Because if you have the letter A twice, for example, it's already in there. It's in there once, so 1 plus 1 is 2. Otherwise, we haven't found it in our existing map, so we just set the frequency of it to 1, because that's the first occurrence we've seen of that particular character. And then what we can do is we can actually set that. So our map, we have this set method here. We set the character, and then we set the new character count here. So that's great. So we've looped through the word S, each character in S, and we've assigned a map which has the frequency of each of the characters. So we can use that information when we're detecting if T is an anagram of S, and we can just simply loop through T this time. So we let character of T, and we want to firstly get the frequency. So let's say the frequency of the character that we're looking for, if that's going to be equal to the S character counter map dot get car. So basically we've got a map and it looks something like this. So for the word A, for the letter A in the word anagram, that occurs 3 times. Then we have the letter N, and then that occurs once. And then the remaining ones, I think they occur once there. So basically we want to, and that's for S. So that's the S words character counter map. So when we're looking at the word T, we're trying to, if it's an anagram, we expect to find that. So for the particular character that we're on in the T word, if we look that up, we'll get the frequency. Now it's possible that that won't exist, and if that doesn't exist, we can handle that case. So we can say if the frequency of the character from S doesn't exist, we can return false, because if the character's not there but it's in T, then it can't possibly be an anagram. Else if the frequency of the character is equal to 1, what we can do is we can simply delete it from our map. Because let's say we look for the letter A and we get the first A in the word anagram, that's in the word T, we can subtract 3 minus, if we have the word anagram and then we have the letter N that's found in the word T, and then we go to look that up in our map here, we know that the frequency of that is just 1. So we can actually go ahead and delete this whole entry here. So we can take the map and then we can delete the character there. So the else case that we have means that the frequency is more than 1. So if we're in the word T and we found the letter A, and then we look at our map in S, the lookup there, and we see that there's 3, we'll just want to subtract 1. So 3 minus 1 would be 2. So we don't need to delete that. So what we can do is we can actually just reset the character. And then rather than this new character count, what we can have is we can have whatever the frequency of the character was, subtract by 1. And then after all of that, we can simply just return our S character count map. And basically, if the size of that is equal to 0, we've gone through every single character. There's none left. We haven't hit any error cases. So essentially, that means we have a valid anagram. So let me run this code here, and actually let me go ahead and submit this code. And we can see that this beats 53%, so it's not too bad. And just to talk about the time complexity here, the time complexity, this is going to be O of n, and the space complexity is going to be O of n as well. So it's better than O of n squared and better than O of n log n. And the reason the time complexity is O of n is because we need to have a lookup. So we need to look up each character in the string. So essentially that's O of n, and then we also need to do it for here as well. So it's sort of like O of 2n, and that simplifies to O of n. And then the get is actually going to be, as we'll see in the hash table video, that's going to be an O of 1 operation. So, and then the space complexity here, this is O of n because we need to have this scar count map. So we have to assign a value for each of the n values there and its corresponding count. So they'll simplify to O of n.